understand what you mean by further up the tree.
Well, I write down 5 and I want a function, but actually 5 is going to be the body of my function.
Oh, yeah.
And the rest of the function is going to sit outside of that.
Yeah, so okay, I see what you mean. So our actions do have, you don't have to construct in an empty hole for all the actions. So plus, for example, you can have the cursor on the 5 and do a plus, and it'll construct a plus on the outside with the 5 as a child. Our calculus, for just technical reasons, doesn't allow you to wrap things in lambdas, because then we didn't want to add a bunch of checks or free variables and things like that. But you could do that, I think. Yeah. So.
All right. Let's thank the speaker. Next up is Karl Crary, who's going to talk about an abstraction theory for modules.
All right, so let me first start by saying that there's very little technical content in this talk because, once I started that ball rolling, there was really no way to stop it. So this talk is one of those talks that's really an ad for the paper. So if you've read the paper, it still would be nice for you to stay here. I like speaking to a room. But mostly this is an ad for the paper. So let me start by going back to John Reynolds' classic paper on abstraction in 1983. So in this paper, type abstraction and parametric polymorphism in the entire world. I love this paper, and I make all of my students read it. I particularly like the fable. If you haven't read the paper, you should at least read the fable, and then you should read the rest of the paper. The paper is also come to be known as the parametricity theorem. I don't really like that name as much because, well, what it's really about is abstraction, and so there's an off-cited. You can't see this at all, can you? Well, anyway, there's an off-cited adage in the paper that says that type structure is a syntactic discipline for enforcing levels of abstraction. All right? And so the idea is that no well-typed program can distinguish between two implementations of a data type, provided that they do the same thing when you're viewing them through the interface. And what that means is that programmers can actually re-implement components of a system without compromising the larger system. So to be really grandiose about this is the mathematical foundation that says that we can develop software with more than one person. So how does this work? All right, so the idea to using the abstraction theorem is that if I have two implementations, I have each implement my abstract data type, some different types, and I'm going to draw a relation between these two and show that the operations of the abstract data type respect this relation. And if that holds, then I can conclude that these abstractions are indistinguishable. Right? Now this relies crucially on two things. One is that the language needs to be strongly typed. If the language isn't strongly typed, then you can ignore the interface, and then everyone is sad. All right, and it also relies on polymorphism being parametric. If you can branch on types, then well, everything at least doesn't come out the same way. You can still tell a story, but it's not quite the same story. All right, so just to give a picture. So many of you have seen this sort of example, but just give one. All right. So here we have, I'm using sort of an ML syntax. So we have a type T, and we have three operations on T. We have an X that belongs to T, a function that takes T to T, and a function that takes T to bool. And we have two implementations of this abstract data type. So one of them implements T as bool, and our basic element is true. F flips that bool back and forth, and then G doesn't do anything to it to turn it into a bool. The other version has an int. It starts us off as 0, and we're going to use the parity in order to say whether it's true or false. So we'll add 1 to flip parity, and then we'll use an is-even function to give a bool. All right, so roughly speaking, the way you would do this then is we define some relation that relates true to all the even numbers and false to all the odd numbers. And then we would show that each of the operations respect this relation. For example, the two versions of x are both related by r, and so forth. All right, but John Reynolds proved this for the polymorphic lambda calculus. He didn't prove this for ML, and that's in some sense the point to this whole talk. All right, so briefly I want to say that what Reynolds' original result gives you is what you could call client-side abstraction. So if I'm developing some sort of abstract data type, then whoever is consuming that can apply abstraction in the way that he or she consumes that. But what we really want is a sort of provider-sided abstraction where when I'm implementing this abstract data type, I can make sure that everybody is going to adhere to my interface, no matter what. Because that's really what protects me from all those other fools I have to work with at my software company. All right, so it's always scary to do a history slide because what you're saying is always wrong. But just to touch on some of the things in modular languages that are most relevant to this. So modular languages are important because that's what gives you provider-side abstraction. All right, so this idea first came about from Clue. Now, Clue was never mathematized, at least not to my knowledge. But I think existential types would have worked nicely. All right, the various modular languages, Modula 2 and Modula 3, added the ability to talk about the fields of an abstract data type with dot notation. And then existential types at Popple back in 1985 actually give a type theoretic account of data abstraction. And you could implement this using impredicative polymorphism and get an abstraction result very similar to what Reynolds did. But this is pretty clumsy, right? You didn't have dot notation. You had to open your abstract type in a large enough scope to encompass all of its uses, and so that didn't work all that great. And then, at the culmination of everything, there's ML in 1986. All right, so ML modules, again, the referees of the paper contested this description, but it's a description I like, so I'm going to use it. All right. So it's a type theory modularity that's based on the idea of strong sums from Martin Loff. And so the idea, I wish I could point here. So if M belongs to the type sigma x colon a dot b, then pi 2 of M, that projects out the second component, that strong sum, has the type B where the first component gets substituted in for x. Okay? And so this gives a notion of dot notation that we can use in talking about the fields of these models. And so in standard ML notation, we'd say, so we have here a structure where type t equals int and val x equals 12, and that satisfies what we call a signature, but is a way of saying an interface that has some type t and some val x colon t. Okay? And the standard ML module system scales up to very powerful module systems, which has been an area of great interest for people like me for some time. Particularly of interest are what we call functors and translucent signatures, and I'm briefly going to give an example of these as well. Okay? So this is some abbreviated actual SML code. So here we have some type of keys. It has some type T. And then there's an equality operation and a comparison operation. And then there's a notion of a set, which has a type of elements and a type of sets and has various operations on that. And then we have a functor. And the functor is important, it's saying I'm going to take in some key, and then I'm going to return a set, but I'm going to say that that type of element is not just some arbitrary type, but actually it's that same type T from the key that you passed in. So we're able to give a signature, which is what's called translucent, that specifies some of the fields of that interface, but not all of them. So that, for example, the type set remains abstract. Okay? And so this pairing of translucent signatures and functors is really powerful. Okay. So abstraction was really the primary purpose for even having the ML module system. And informally, we believe that the ML modules work very well for abstraction. So we have lots of good examples that were worked out in various papers. And in fact, there's lots of software projects that use this very effectively. But what we don't have is any kind of actual mathematical story that justifies saying this really works. So the original Reynolds result doesn't apply to the system. And in fact, there isn't any published proof of an abstraction result for any ML-style module calculus. And so, well, spoiler alert, it turns out it works. So, so that's what this paper is about, is finding out that, in fact, this thing that we always thought works. But actually, I think the details are a little bit interesting, and so it's a pity that I can't do the details in this talk. But I'll gesture at them, and that's the best we'll be able to do. Okay. So I want to front load this with the related work. So there's two pieces of work that are particularly relevant to this. So in 1995, Poppel, Xavier Leroy had a paper on applicative functors, and in that paper, he postulates an abstraction principle. It's not proved in the paper, but it's used to prove a variety of important corollaries. And his purpose in that paper was to show that if you have a functor application in your paths, this is a technical idea from the module literature, if you have functor applications in your paths, it turns out that that doesn't spoil data abstraction, at least if this abstraction principle holds. There's some technical differences between the language that he used in this one. It's an older module language, and it doesn't have all the bells and whistles that were developed later. And also, it used a denotational approach instead of a syntactic approach. So that's one sort of related result. The other thing I want to mention is this delightfully named paper called Effing Modules by Andreas Rosberg and others. And in there, what they did is they looked at viewing the entire ML-style module system as something you can elaborate directly into some sort of polymorphic lambda calculus. And the idea there was to argue that modules are at least as elementary as all these things that we like from the polymorphic lambda calculus. But you could also take that as basically as your definition of the module calculus and inherit from that some view of abstraction just by taking Reynolds' original theorem and viewing that through the lens of this elaboration. So this is a perfectly sensible thing to do, but one thing that that this paper didn't do is actually show that this elaboration provides what you think you're getting with ML modules, because it didn't have an independent story of what the ML modules abstraction meant. And so basically one way you could view this paper is as a way of substantiating that implicit claim that the Effing Modules paper made, that they really were providing the same abstraction guarantees as ML modules. Okay, so what is this work about? So this work is about an abstraction theorem that applies to ML modules in the system, and the module calculus that we're using is quite expressive. So we have higher order modules. There's both generative and applicative functors. There's type effects, and I'll say briefly what that means a little bit later. And it also supports the full singleton kind calculus, which is key towards understanding this notion of translucent signatures that I alluded to earlier. Should also mention that the core language does support recursion, which is always a tricky thing in dealing with these sorts of things, but there's a lot of important things it does support, particularly state. And in fact, one can't even really say that state is orthogonal to the typing effects that we're talking about here, so that's some future work. Okay? I should also point out that the module calculus that I'm using, which won't be in this talk anyway, but is in the paper, is still a core calculus of modules. We still rely on the elaborator for certain things. For example, we use it to rely on some things that type theoretically are complete nonsense, like open declarations, but also some things that we just don't have the type theory to explain really well yet, such as ML signature coercions. And finally, everything in this work is formalized in Coq. All right, so really briefly, here's how we tell the story of abstraction. Many of you know this already, but I like to tell this story, so I'm going to do that. So the way that we tell the abstraction story here is first we define some notion of contextual equivalence. And that can be defined one of two ways, right? One popular way is to say that we universally quantify over all closing contexts and say if you're two pieces of code put into that context, they do the same thing regardless of what closing context you choose. So you can't possibly write any larger program that when you embed these programs into them, it tells the difference between them. And this is sort of the gold standard for equivalences, right? You can't really do anything broader than this. Equivalently, I want to mention this because this comes up a little later in my talk, you can also define contextual equivalence as the course's congruence consistent with execution. Okay. Now, so first you define contextual equivalence, but because it quantifies over all these closing contexts you know nothing about, it's really hard to use for anything. And so then you define logical equivalence. The nice thing about logical equivalence is it actually is governed by the code that you write. So it takes the types of the code, and those types tell you what sorts of experiments you can run on the code, and those types then govern this, the definition of logical equivalence. And we say that equivalent expressions are ones that produce equivalent results in some appropriate sense under equivalent type-driven experiments, again, in some appropriate sense. All right, so then you prove that contextual and logical equivalence actually are the same thing. Contextual is gold standard, but logical is nice to use. And so then, profit. All right, so let me give a really quick example of how the profit part works. All right, so here I'm going to pretend that I have existential types. Well, actually, in the paper, I do have existential types. So if we want to show that two existential packages, rho E and rho prime E prime, are indistinguishable, right? That means to say they are contextually equivalent. That's the little double squiggle, right? Then it's sufficient in order to show that they're logically equivalent, which is the double arrow, right? And so that's the main result that says that logical equivalence and contextual equivalence coincide. So now it's good enough for us to show that these are logically equivalent, and the way that we do that is, well, we don't have to require that rho and rho prime are the same, because that's no fun. That means you can't ever redefine your abstract data type with some new carrier type. But we come up with some relation R between rho and rho prime, and we show that E and E prime are logically equivalent, roughly speaking, at R for alpha and tau. You have to define what that means. Okay, so that's kind of how this sort of thing is supposed to work, and that's how you learn that two abstract things are indistinguishable. So what makes this hard? All right, so now I'm halfway through and getting to the point of the talk, I guess more than halfway through. All right, what makes this hard is three main things. So first of all, modules are mixed phase objects. So in Reynolds parametricity, polymorphic functions, which abstract over types, and regular functions, which abstract over terms, are treated very differently. But if you write, say, a functor, which abstracts over a module, that has both type components and term components. And so these mixed phase objects, we have to somehow cope with the fact that they need to be treated both as a type constructor and as a term simultaneously. All right. Second of all, there are typing effects. Roughly speaking, typing effects, don't have time to really go through the module system here, but it's not new to this paper. And roughly speaking, we use sealed modules. Those are the ones which are abstract and you can only use through the interface. Those are somehow impure. The idea is that there's some daemon who comes in, modifies your module in order to change things around in such a way that you don't know what the types are anymore. Of course, that doesn't actually happen, but that's sort of notionally the effect that's going on. Right? And since we have pure and impure modules, that gives rise actually to two notions of equivalence. Equivalence at impure modules and equivalence at pure modules. You have to cope with that. And then finally, the underlying type theory that involves these singleton kinds, which we needed to talk about translucent signatures. This is actually really quite tricky in its own right, and that has to be dealt with as well. So those are the three main things that makes this hard. All right, so what do I mean by typing effects? All right, those sealed modules, if in ML this is written, standard ML, this is written with a colon greater than. All right, a sealed module is one that's abstract. You can only use it through the interface. And we view that as an effect which helps us track that sort of behavior through functors. Right, this is an idea from Derek Dreyer's module calculus paper from Popple in 2003. So as I said before, pure modules are unsealed, impure modules are sealed, and we can see here that unsealed modules are much easier to distinguish. So this is the same example before, but if I say you don't have to go through the interface, well, now you can really easily tell that these two things are different. You can even distinguish them syntactically just by writing some code that relies on t being bool or int, and then it won't even compile with the other one. Okay. All right. So singleton kinds they arise because of type specifications. So if I say type t in a signature, then I'm saying that t has kind type. If I say type t equals int, then that says that t has the kind singleton of int. And this gives rise to a subkinding relation. Any singleton is a subkind of type, but it also makes type equivalence context sensitive. So obviously, if alpha is singleton int, then we can say that alpha and int are equivalent, but if alpha is an arbitrary type, then we can't say that. You can't be serious. Oh, all right. And other things happen as well. All right. So contextual equivalence is, this isn't novel, but it's a little bit interesting. It's not how it's usually done, and I don't have time to talk about that. So let's see. So how we code with the singleton kind calculus. So we have a notion of pre-candidates, which your typical candidate is the pre-candidate at type, so that's some relation between values. And then we can lift that up to higher kinds by saying we have functions that generate such things in an appropriate way. Call these pre-candidates because we don't at this point check that they have the appropriate closure conditions. Okay? On kinds, what we say is that we have a quadruple that belongs to the interpretation of K. By the way, everything here in order to tell a simple story is over closed expressions. So C and C prime are two constructors that belong to K. And Q and Q prime are two candidates that relate those. And we need to be able to say when two candidates for technical reasons are equivalent. But because equivalence is not context driven, we can't just use set theoretic equivalence for that. We have to set up a per for this. Also, I'll mention in the paper, getting the proof to go through requires some very delicate staging. We have a notion called model regularity in the paper. Okay, so types are actually pretty standard. I'll skip that. And then finally, so for signatures, what do we want to say? So if a signature contains modules, and a module is a hybrid of a term and a type, so a signature is a hybrid of a kind, a type, and a kind. And so what we're going to say here is that V and V prime and some pre-candidate Q belong to the interpretation of signature sigma, provided that, well, V and V prime are appropriate modules to belong to that, and also provided that they are viewed as logically equivalent. And furthermore, Q should be some candidate that relates the static components, which we write there as first of V and first of V prime, the static components of those two modules. So that's where we take into account the fact that these are mixed phase objects. Okay? So this is an idea that goes back to Harper, Moji, and Mitchell in 1990. The idea that we can take a model and we can separate apart its static and dynamic components. That's its type-ish stuff and its term-ish stuff. And so once we do that, if we separate out the type-ish stuff from this module, then we can come up with some candidate to relate the type-ish stuff of these two modules. Okay, so we can define our logical equivalence here, and what I mainly want to gesture at here is, so the first is fairly standard for any notion of logical equivalence. The second one says that if we want to say that M and M prime are logically equivalent as impure terms, then there should exist some Q, some candidate, that is able to make those things work out to be the same. If we want to say that they are logically equivalent as pure terms, then that Q can't be any old Q. It has to be the standard interpretation, logically speaking, of the static portion of that module. Which is to say, let's say I'm defining my type T to be equal to int. The relation that relates it has to be the actual standard logical interpretation of int. Okay, and I need to mention that for the purpose, we'll skip that, purpose of this example here. And this is pretty much where I'll conclude. So here we have, basically, it's an abbreviated version of the example before. All right, so we have some type T, val x colon T and F, which produces a bool from a T. And I have three implementations of this. Right, one of them uses bool, true, and ID, so nothing much happens there. The second one we're implementing, the second and the third, we're implementing T with int. And in the first case, we're using even numbers and odd numbers. In the third case, we're using even numbers, or 0 and non-zero. Okay? And as impure modules, all these things are contextual equivalent. And we can show it by drawing an appropriate relation between bool and int, or between int and int. But as pure modules, these are all equivalent. So they're easily distinguished by the context that says, well, project out the field f and then apply it to some non-zero even number, like 10. Okay? And so we can see that they won't be contextually equivalent. How does logical equivalence fail, which it has to since it coincides with contextual equivalence? Well, M1 and M2 don't have equivalent static components, so it's a non-starter in that case. More interestingly, M2 and M3, they not only have equivalent static components, they have identical static components. All right? But the Q that relates them is not the standard equivalence on int. We have to pick some other relation, which isn't the public equivalence on int. All right? So these things are going to work out to be inequivalent for that reason. All right, so I think that is, oh, right, and formalization. So all this is formalized in Coq, and the formalization is really great. And that's it. So I hope that whets your appetite to read the paper. Thank you.
Yes?
Hello. Yeah. How do you compare to Marc Lasson's work on parametricity and realizability in pure type systems?
I'm sorry?
Realizability and parametricity in pure type system. There's a PhD thesis on this by Marc Lasson.
I don't actually know that.
You don't, so he actually, I think it's very close to what you're talking about here. Maybe we can talk about it later.
All right, I wish I hadn't informed answered your question, but I don't.
Okay.
Oh, I should be here. Yeah.
Okay. So your logical relations looked a little bit like the ones from the non-parametric parametricity paper. From Nice and Dreyer and so on. And I'm wondering if there's a relationship, like maybe you could encode what you've done into that system, and be like the sealed modules would be the ones that were wrapped in their terminology, and then the unwrapped ones were the...
All right, I hadn't thought of that connection. What you're saying is plausible. I'd want to look at more carefully to give a definitive answer. Is Derek here? Yep. What do you think, Derek?
Oh,
Derek even has a microphone.
We can take that question offline. I have a question of my own. So, so in our paper from Pablo 2003, there was a failure of abstraction in that type system, which was that if you had an applicative functor, like the set functor you showed, and you applied it to two different orderings on integers, say, less than and greater than, then you would get out the same set type, and that would that constituted a violation of abstraction. So I'm wondering, what does this result have to say about that?
Yeah, so the solution that we had in the paper, as you recall, is we had this notion of weak sealing, where we said that something generated like a little bit of an effect. Not enough of an effect to carry through some operations, but enough of an effect to carry through other operations. And I don't model weak sealing in this paper. I think I know how to do it, but it's not in this paper. So this paper doesn't have anything to say about that particular sort of abstraction failing.
But you could still use use sealing at the functor level to seal the whole set functor with a signature that
that's right. You could seal the whole set functor as an applicative functor.
Right.
So if that's what you're getting at, then yes, I do have something to say about that. But if you wanted to force you to make it into an applicative functor at a particular type by putting weak sealing in the body, that's what this doesn't have anything to say about right now.
Sure, yeah, I just mean you could get that same failure of abstraction even if you just used strong, whatever you're calling impure sealing at the functor level. So I'm wondering how you avoid that problem given that you have the abstraction theorem. Or maybe whether this abstraction theorem says anything about that example. I guess that's the question.
I think maybe we should sit down and look at it, because I think I'm maybe too tired to figure it out standing in front of a room full of people.
All right, sounds good. So let's thank the speaker once again. And I believe we now have a lunch break, so I guess follow the route, but for those who want to go later, you just go out into building 44, then go up a level, and lunch should be there. All right, thanks.